This episode of the HVAC School Podcast is made possible by the Carrier Corporation. And I want to give Carrier some props because recently they had a recall. Normally you'd think that would be a bad thing, but the way that Carrier handled the recall was really exemplary. They had an issue with some of the Carrier green speed systems with some boards that had the potential of overheating. Now, it caused zero property damage, zero fires, but they knew they had an issue because some of the heat shields were coming back where they showed that there was some excessive heat. And so they did a quick recall. They gave us a list notifying us of the customers that fell under the recall, the systems that we had installed. We were able to go out really quickly and take care of it. And that's exactly what you want to see from a manufacturer. There's no manufacturer that's going to be perfect all the time. But the most important thing to me is that they support their products, they take care of their customers, and they communicate with their contractors. And Carrier's always done a good job of all of those with me. We're also proud to have Testo Tools as a sponsor. I talk a lot about Testo. A lot of guys kind of razz me about it, but I am a big fan of Testo, and you can get all of the great Testo products by going to TruTechTools.com. Use the offer code GetSchooled for a great discount. Testo Tools makes great test instruments, all the way from very inexpensive all the way up to the highly premium products that they make. And you will find all of that at TruTechTools.com. I also want to thank our newest sponsor, which is RectorSeal. And RectorSeal makes a lot of different products, but one I want to talk about real quickly is their no-vent line of tamper-resistant caps. And so one thing that they point out is that the actual international code, the International Mechanical Code, points out that a special tool should be required in order to remove these caps. And so a lot of municipalities are starting to adopt the International Mechanical Code on this subject. There are some manufacturers that make tamper-free caps that just use a Schrader core removal tool. And if the point of the tamper-free caps is to keep people from tampering with it, then using something that kids use to take the cores out of their bicycles isn't necessarily going to be considered a tool that is a specialty tool. So that's why RectorSeal makes their no-vent product with a special tool that is only sold to licensed HVAC through HVAC distributors. So thank you to RectorSeal for sponsoring the podcast, and check out the no-vent tamper-free caps.
And now, the man who graduated high school at 16, and instead of going to college, chose to become a HVAC technician. Yes, we all question his sanity. Brian Orr.
Yes, my sanity may be in question in many ways, but the one thing that I will never regret is going into the HVAC trade, which happened very much by accident, actually. My father was a licensed electrical contractor and building contractor. He both worked as an electrician and then as a building contractor later in his career, which he still is today. And I didn't want to follow my dad's footsteps too much. I wanted to kind of forge my own path. So my dad and I were sitting down at the kitchen table when I was 16, just graduated high school. I had graduated 2 years early. And he said, "All right, son, you're always gonna want to have a trade in your belt. You can go to college or do whatever you want later, but let's start with a trade." So we looked at the pamphlet for the local trade school, and he said, "Well, air conditioning guys, they do pretty interesting work. I think they make pretty good money." And off to the races I went, and I've never regretted it. I really like this business. Another thing that I'm very interested in right now is building performance. And so today's podcast is actually a rebroadcast of an episode that I heard first on the Building Performance podcast. So that is Corbett Lunsford's podcast. I've had Corbett on the podcast once before on HVAC School, and I listened to his podcast regularly. And there was an episode on there where he did an interview with Lou Harriman on moisture in things, moisture in air and moisture in things, and how to control moisture in air and moisture in things. It was really interesting. I learned a few things I had never really considered, frankly. It's a fairly technical episode, so it really gets into humidity and moisture in a way that you probably never thought about it before. So I think you'll enjoy it. And also, I'm going to suggest that you go and subscribe to Corbett Lunsford's Building Performance podcast. Really, no matter what segment of the industry you're in, there's just a real intersection between building performance and HVAC. He's got a lot of really good information there, but this one in particular very much applies to what we do day in and day out. So thank you to Corbett for allowing me to do this. He's been very generous with me, and I really suggest that you check out his website, check out his podcast. You can look him up online. He has a really good YouTube channel, and you can find all of that by going to buildingperformanceworkshop.com, buildingperformanceworkshop.com. But here we go. We've got Corbett Lunsford interviewing Lou Harriman for his podcast, the Building Performance Podcast.
Welcome to the Building Performance Podcast from the Building Performance Workshop. I'm Corbett Lunsford, and we are talking today again with the amazing Lou Harriman, who is the founder of Mason Grant Consulting in New Hampshire, and also the author of multiple ASHRAE books on humidity control. Lou, thanks so much for talking with us.
It's a pleasure to be here, always.
So, listeners, Lou and I were having a conversation. We're in his home, and I started asking him about humidity control, and then I said, wait, stop. We need to record this. So we were in the middle of kind of getting into the conversation about humidity. I wanted you guys to be able to hear what Lou has to say because he is one of the world experts on moisture in buildings. So when I asked you, how about drying? Like, what exactly is it? How do we start to think about it? You said that there's a basic principle that we start with, which is?
Well, when you're thinking about drying, the first thing you want to be conscious of is whether you're talking about drying air or whether you're drying stuff. Because a lot of the confusion about dehumidification comes from the desire to dry stuff, which is different, and a lot of the confusion about drying stuff has to do with dehumidification in a psychrometric chart, which is very confusing on both sides of that divide. So it's useful, very useful to think, first of all, when you're thinking about drying, start with, am I talking about taking water out of air, or am I taking water out of stuff?
Okay.
Begin with that.
And then, so my follow-up question to that would be, if inside we dry out the stuff, wouldn't that, as a side effect, dry out the air?
Absolutely it would, because there's no getting around the fact that water in stuff, moisture in stuff comes into the air, and moisture in the air goes into stuff. And that happens dynamically all the time. All the time. No matter what's happening. Even when it's very dry inside, there's some statistical probability that some of that moisture in the air, the humidity in the air, will get into stuff. But there's a much bigger probability when the air is quite relatively dry inside that the water is going to be coming out of the stuff and going into the air. Mm-hmm. But it's going in both directions at the same time.
In one of the previous podcasts that you were on, we talked briefly about the fact that up till the 1990s, everyone assumed that the hotter it was outside, the more moisture there was in the air. And then you realized when you were part of a research team that actually measured things, that was all wrong. What else have you found out that kind of is assumed by engineers that actually, once we apply research to it, is not true?
One of the biggest gee whiz forehead slappers in my career, in my working career, has been understanding what happens in a home when you change its temperature. Well, let me put it another way. Let's start with the fact that in the engineering community, we think about absolute humidity versus relative humidity. Absolute humidity being the amount of water in the air, and the relative humidity being the amount of water in the air compared to what that air could hold at that same temperature. In the humidity control business, geeky folks like myself have always said that while you might have differences in relative humidity throughout a building, because the temperature changes throughout a building, the dew point, the absolute humidity, stays pretty much constant, independent of the dry bulb temperature. And that's wrong. That's completely wrong. How I found that out is measuring things and monitoring things. Much to my surprise as a guy who's spent a lot of time in desiccant dehumidification, is that it doesn't take a big change in the amount of total energy in the system. In other words, it doesn't take a big dry bulb temperature change in a house to make a difference in the dew point in that air, because moisture does come out of the material and it goes into the material based on very relatively small changes in dry bulb temperature. For example, I'll give you a couple numbers on this. If we have a dew point of, let's say, 45 degrees Fahrenheit, which is a fairly dry condition in the summertime in a house, that's an air-conditioned house. And if you don't have air conditioning, and if you don't have heating, you're just watching the temperature get warmer in the house because it's heating up, because we're not doing any cooling. And if we were to go from a temperature of 70 to, let's say, 80 in a house, the dew point might go from 45 to 65. The absolute amount of moisture is going to go up by a lot, by 20 degrees of dew point, with perhaps a 10 degree Fahrenheit difference in dry bulb temperature in the absence of any other dehumidification or humidification or heating and cooling equipment.
And that is because moisture is going to be drawn out as the dry bulb temperature rises in the air. It's going to pull moisture out of stuff in the house.
Yes.
And that's going to exacerbate the problem.
Well, I don't know if it's a problem. It's either a problem or not, depending on the range of values you're talking about. But that was the unexpected thing. So you asked for an unexpected thing that comes from measuring things. That was a big one for me, probably sometime between 5 and 10 years ago. That became very clear to me. We've always known, of course, if you change the temperature of stuff, in the absence of any other change, you change the temperature, you're going to mobilize water. It's going to want to come out of stuff. What was unexpected is that this happens with a 2, 3, 4, 5 degree Fahrenheit difference in average air temperature. That was the big gee whiz to me. But I stress that we're talking here not about a commercial building with a bunch of tile floors. What we're talking about is a residential situation where you have absorptive materials like wallboard, like carpets, like fleecy materials for upholstery, like books, so that you have a lot of surface compared to the air volume that's enclosed. So it's going to be different in a courthouse. In a courthouse where there are huge, wide open areas, and it's a lot of ceramic tile, and you don't have much in the way of fleecy materials. In a house where you have a lot of absorptive materials and a relatively small amount of air, a small change in temperature will create a significant, a larger than expected change in the absolute humidity in the house in the absence of any other factor.
Which that's reality, right? Oh, no. There's more factors.
Actually, no, because the problem is that there are lots of other factors.
All right. So we'll set this aside for a moment. On a related note, people say there's this myth, and I don't know if it's true or not. I'd like to ask you since you're the expert. They say that a furnace dries out the house, and radiant is preferred because it makes the house more moist. And knowing as much as I know about this stuff, that seems like it's not actually true to me. Is it actually true, or what's the deal?
I think it's fair to say that it's true in some respects and completely false in others. And that's like a lot of things in building technology and building science, is that these sayings and thoughts persist because they have a great deal of truth to them, and yet by themselves they can be very misleading. So let's take that one step at a time. If we talk about a forced air system, a furnace. So it's a furnace. It's going to distribute air throughout a building, and the mythology is that that's going to make a dry environment. Well, it's certainly not going to make a dry environment if there's a humidifier on the furnace. If there's a humidifier that's going to add moisture, then it will be whatever the humidifier can pump in. But it certainly is true that in the absence of any other factors, ductwork tends to leak. We know this. Ductwork
I've
leaks.
Heard about that, yeah.
I think you know something about that, Carl. You quantified that many times. So because ductwork leaks, a duct system will pull dry air from outside in the wintertime into a building, because you will have areas of local negative pressure and areas of local positive pressure. But the pressures created by a fan are so big, they're 100 times greater than the pressure created by stack effect, basically. So you will create pressure differences, and that will result in dry air infiltration that probably will not happen as much in a house that's heated by radiant heat. So yes, it's true that houses with furnaces tend to be drier than those with only radiant heat, but if the radiant heat is also well ventilated, then the house with the radiant heat might be a great deal drier because you might be getting adequate ventilation from outside.
So let's say all things being equal, a house is airtight, insulated, ventilated to the standard that is enforced by the 2012 IECC, blah, 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 and one of them has a forced air furnace and one of them has a boiler. Based on your logic, it sounds like not running the humidifier, that they would be the same humidity. Is that correct?
They will be the same. They will be the same. And they'll both be pretty good because to meet the requirements of the energy codes, that's going to be a heat recovery ventilator. Yeah.
Interesting.
But they will also be drier. They will be drier than many houses because of the fact that they are being ventilated to code. Unless you're in the Canadian North or in the Northern Tier, let's say Minnesota, you're probably not going to use an enthalpy heat exchanger to do the ventilation, so you're probably going to be losing humidity from inside. So when you're ventilating in the wintertime to code, continuous ventilation of 90 to 65 to 95 CFM in a house, that's going to be a continuous stream of air that will always be drier outside than what it is inside. So both the radiant heated house and the furnace heated house are going to be drier unless there's humidification or unless there's enthalpy heat recovery, which is to say that not only are we recovering heat from the exhaust air, but you're also recovering humidity from the exhaust air.
So since we're going down this path, and we will get back to how to think about drying in just the principles of it, because I'm really interested in that. The enthalpy dry, and we're talking about ERV, an energy recovery ventilator, versus an HRV, which is just heat recovery ventilator, which is like sensible, right? So first of all, there's a big argument about which one you should use in mixed climates. I'm from Chicago. You're from Portsmouth.
Climate, right.
We've got people in Texas has some heating, I'm sure. Atlanta is heating dominated, but they still have a lot of air conditioning. Which one are you supposed to use is the question number one. Number two, the manufacturers seem to be kind of building these hybrid systems that can kind of do both. They can do one or the other. And so do those words still apply, ERVs versus HRVs, or are there kind of hybrids now that are kind of in the middle? And which one are we supposed to use and when?
Beats the heck out of me. It's still a pretty complex question, partly because, as you say, the hardware is evolving. The big deal here to me with ERVs and HRVs is actually not so much a question of whether it should be recovering enthalpy or whether it should be recovering just sensible heat. You have to know that the first part of my career was selling enthalpy heat exchangers, so I'm a big...
Oh, no. He's biased.
So I'm a big fan of enthalpy heat exchangers for many applications, just not for houses. And that's because usually humidity is a pollutant that you want to get rid of in a house more hours than you don't. So if you have air that is drier outside, that's probably what you want more of the time than the humid air going out. But it depends. It depends on whether you're talking about public housing, where you're talking very densely occupied, highly humid indoor environment.
Hard to tell what people are going to do when they're living in that environment.
Well, and how many people they're going to be and what they're doing, as opposed to two semi-retired, yuppies living in 4,200 square feet, where it's quite dry inside because nobody's doing any cooking in there at all. So it's very different, and it's difficult, I think, therefore, to say we should be doing this versus that. But in general, I think enthalpy heat exchangers are not the wonderful panacea that I certainly believe they were when I, 1976 to 85, when I was selling those things for hospitals. There, it's all the time. There's no question that everyone should be using enthalpy heat exchangers. But in a house, I think the question is more nuanced. And in terms of the technology, what you really want to avoid is you want to be able to modulate the amount of recovery so that you're not recovering something you don't want to recover. You don't want to recover moisture. A lot of the time in a house, over 87, 60 hours of the year, is a lot of the time you don't want any of that humidity back in the house. To me, it's less a question of the membrane technology and more a question of the controls.
So getting back to the principles of how to think about drying, we've got the two different segments. We've got drying stuff and drying air. Since we're talking about buildings and specifically residential buildings in what we were just getting into, why don't we talk about drying air for a minute? What within drying air are important principles that are kind of basics for everyone to understand?
I think the most important thing to think about when you're thinking about drying air, in other words, you're looking for comfort. You're looking to prevent significant damage to a house. You're trying to keep the humidity, the amount of water vapor in the air at a comfortable level. And if we're talking about taking water out of the air, we're talking about the cooling season when you're taking it out of the air. Most important thing to think about is where the humidity is coming from, because that will tell you a lot about the most cost-effective and the simplest way to take too much water out of the air is where it's coming from. So in a residence, as opposed to a commercial building, you have a couple sources. The biggest and the most important one in a residential situation, single-family residence, is cooking. Why is that different than showers? People think a lot about showers, and you kind of idea, hey, you're going to put a lot of humidity in the air in showers, and people grow mold because they don't take
too many showers.
They're taking too many showers. You're much too clean, and so therefore you get mold. It's like, if you think about the time that you're taking a shower, it's not a lot of hours. whereas cooking can be quite a lot of time. And it can be a whole lot of water into the air that may or may not be exhausted. Now, if you've got a shower or toilet exhaust in the bathroom and you're not using it, then yeah, you'll have let's say 10, 15 minutes worth of high humidity in there. But with cooking, a 10-minute cooking session, that would be a pretty short one. Whereas some people can cook for a very long time, or if you are, from the Indian subcontinent, you're going to cook for a long time to get a good, effective, curry and so forth. If you're from Latin America, you might have, sauces that you want to cook for a long time.
If you're going to make coffee Lou Harriman style, it's a little bit more complicated than just...
Well, that's true, too. It'll take a while.
It's good. Anything good takes time. Yeah.
Anything good takes time, and there's going to be water vapor evolved from that, and we don't always remove it from the house. So that would be number one principle of keeping the house at a comfortable humidity level and taking the water out of the air is exhaust at the source. Exhaust at the source when the source is producing water vapor. So in a bathroom, you'd like to make sure that if you're taking a shower or taking a bath or drying clothes in the bathtub, that you are exhausting that extra humidity. In the kitchen, you'd like to make sure that you're exhausting from the kitchen when you are cooking. Okay, so those are two big things that you really don't have to worry an awful lot about in an office building. There are very few office buildings that have a lot of people cooking curries, and they're or making boiling pots of pasta for 20 or 40 minutes or so. Very rarely happens. And not too many people take a shower in the middle of the office. That's a rare thing to have happen. So
it's a sad truth of America in the 21st
century. Sad truth. Maybe we could benefit from that. So that's one thing that happens in a house that doesn't happen in a commercial building. But the thing that does happen in a house these days, exactly like a commercial building, is a perceived and a real need for ventilation air to dilute indoor air contaminants. That has been at the root of a lot of the humidity control problems in commercial buildings, which is to say humidity too high, because we have ventilated without drying that ventilation air. And that's what we are having now in houses, is that we are ventilating without dehumidifying, because there's no code that requires us in either commercial buildings. There's no guideline that in commercial buildings or residences that says that you should dry the ventilation air. So we don't, because nobody wants to spend extra money for stuff that's extra. And therefore, we end up with more humidity in the house when we ventilate, because if you look at the 8760 hour, the full year, 8,760 hours is what we have in a year. And if we look at even a mixed climate, everything except a very, very dry climate, of which there are very few, the bulk of the load that you have to take out of the incoming air in the north. The
load meaning the actual water that's coming in on
the cooling load, the heating load, the dehumidification, the humidification load. It's all about the ventilation air. And in the case of dehumidification, in all except far northern climates and high altitude climates and desert climates, the ratio of humidity to take out of that ventilation air compared to sensible heat is anywhere from 3 to 1 or 5 to 1. In other words, in the Boston area, for example, you're going to have to take about 5 times as much load in terms of dehumidification out compared to heat out of that incoming ventilation air. So you've got a cooling load. You have to cool the incoming air, in Boston, but you have to dehumidify it too. And you have to do a whole lot more dehumidification of that air than you have to do cooling of it.
All right, so I've got a really, really quick tooltip corner here, and I've addressed similar things to this in the past, but I just want to kind of nail this down. So we talked in the episode with Jim Bergman about checking the charge without gauges, and a couple things that you really need to be able to do in order to check the charge without gauges. And like I said, I know I've talked about this before, but I think it's really important for you to know this. You need to have an accurate line clamp. So a line clamp that measures line temperature very accurately. Thermistors are better than thermocouples, although they're both better than what we were using years ago. I remember when I first started in the trade, we used to actually duct tape or electrical tape, or take a piece of Armaflex and tape it around a pocket thermometer to measure superheat. That's how we started out doing it. And what I tell people is, hey, at least we were checking superheat when I started. And so you need to have a good way of taking a line temperature. And a thermistor is better than a thermocouple. And you need to also have a way of measuring wet bulb and dry bulb air temperatures reliably. And one of the easiest ways to do this inexpensively, so if you just want a bare bones, bare minimum way of doing this reliably and regularly for the lowest possible investment, so you're a new technician out there, you realize that you don't have a good way of doing this, but you want to be able to try out the things that we taught in the episode with Jim Bergman about checking the charge without gauges, then I'm going to suggest that you get a Testo 115i. That's the clamp. That's the Bluetooth clamp. I mean, it's a really high-quality Bluetooth thermistor clamp. It does a really good job. When I say really high quality, I mean, are there things out there that are maybe better, maybe a little more accurate? Sure, of course. It's not a super expensive product, but for what you're getting a thermistor clamp, a Bluetooth thermistor clamp at an excellent price, especially if you go to TrueTech Tools and use the offer code GetSchooled. But then also, if you want to measure the air temperature, wet bulb, dry bulb, you can use the 605i, and that allows you to do it actually in the duct. So you can actually calculate, if you get two 605i's, you can calculate delivered capacity. But even if you don't want to do that, just get one 115i and one 605i, and you have what you need in order to measure, in order to test the system and see if it's functioning without gauges, so long as you've done a prior benchmark or somebody else has. It just gives you a really, really good tool to start doing that and start practicing it, and I think you're going to find that you'll learn a lot through the process. All right, here we go. Back to Corbett.
Let me break it down. We're bringing in air from outside. We're exhausting air from inside to outside. We're rubbing up against each other, and we've got an HRV that's just going to transfer the heat, which is good, but you're saying that it's not even a drop in the bucket compared to the amount of moisture that we're going to want to take out of that air that's coming in. Is that correct?
That is correct, but when we say we want to take the water out of the air, it still depends on what level of humidity we want to have inside. And the fact of the matter is, we people can be quite comfortable at a very wide range of humidity levels, of absolute humidity levels, and even relative humidity levels. We can be comfortable at a lot of different levels.
What are those levels? Like, with some guidelines we've heard in the residential market, between 30 and 50% relative humidity in the wintertime is nice. Is that the expert's opinion as well? And what about in the summertime?
I think if you look at it on an annual basis, something between 30% relative humidity and 60% relative humidity would be the center of a rational comfort zone for a house that's being held between 68 degrees Fahrenheit and 78 degrees Fahrenheit. 68 to 78 might be a range. And within that range, 30% relative humidity in the wintertime might be kind of a lower level of comfort at 68 to 72. And in the summertime, at 72 to 78 degrees Fahrenheit, probably 60% RH would be an upper boundary. We have that range. So when I say load, what I'm talking about is if you wanted to keep a constant humidity level inside.
Constant absolute or constant relative?
Constant absolute level.
Okay.
So we don't care about relative humidity when we're talking about load, because relative is relative to temperature and it squishes around. It's squishy. When we're talking about load and taking water out of there, we have to speak in absolute humidity terms. So if we wanted to keep a constant absolute humidity, then under that circumstance, we would have to take much more humidity out of the incoming air on an annual basis than we would taking heat out of the air in a mixed climate. In a southern climate, it's much closer to the same number, but it's still maybe 3 to 1, not 5 to 1. So there's still one heck of a lot more humidity in the air if we wanted to keep a constant level inside. But we can tolerate a lot of slop, and that's what we get. But the big point, and the reason I want to mention this, is that when there's a humidity control, quote, problem, unquote, when it's an uncomfortable amount or an unproductive amount, or if we have moisture condensing inside or things like that, then we have to speak in terms of absolute humidity. And then the place to put your mind is the ventilation air, because that's where that constant load is coming from. So you mentioned we've got the HRV. What percentage of the houses in the United States have an HRV? I'd submit it's less than 5%.
I was going to guess one.
Yeah. So I don't think we have those devices in most houses. So therefore, especially when we're talking about exhaust, kitchen exhaust in particular, when we're talking about houses with no makeup air system at all, with no ventilation air system at all, what we're talking about is exhaust that pulls in humid air from outside. And that's the air that's giving us so much trouble, is when we're exhausting a lot of air, but we don't replace it with dry air. Mm-hmm. So that's
Someone represented an idea to me that I thought was kind of brilliant, which is to have the return plenum be kind of a room at the bottom of a closet, like a little cavity, and to actually just have an outlet in there that you plug a dehumidifier in that room and have a duct through the wall to outside. So that is, first of all, is that a valid way to dry the incoming air in this kind of scenario? And secondly, how else would we dry the air that's coming in, since we're really not, as you mentioned, not doing this at present?
That can work, and it can fail miserably. One of my colleagues in Florida, he's a registered professional engineer and a forensic engineer, and he was called in for 400 apartments where that was the basis of the design. The idea is you cut a small hole in the exterior wall, and that comes into a plenum in which there is mounted a conventional cooling-based Sears or Kenmore or somebody's dehumidifier mounted below an air handler. And that's the idea, is that you're going to more or less dehumidify the return air and the incoming air blend. And that can work, but it is often problematic. And the reason is because that dehumidifier may or may not be effective. In other words, it may or may not take moisture out of the air. And number two, it may or may not take moisture out of the air when you want it to. The question is, how is that little guy controlled? Is it controlled with a humidistat that works or one that doesn't? And is the humidistat mounted inside the cabinet of the dehumidifier? So it's sensing the humid air right next to the cooling coil, and therefore it cycles on and off? Or is it mounted outside, the way none of them are? Except the one that I have in my basement, which I had to modify, so it didn't do that. So there are reasons that design should work better than it often has. There are often other cases where it's worked just fine, where you have a smaller amount of loading, where you have a higher occupancy, where you have people that adjust that humidity sensor in the dehumidifier, where you have people that actually clean the filter on the dehumidifier so it gets air instead of just slowly clogging with
life
crud.
Is so complicated.
You asked, is that what we should do, or should we be doing something else? What we should be doing is something else. What we really should be doing is using hardware that doesn't exist. And that hardware would be designed so that it's a little miniature makeup air system for residences. And it would humidify in the winter, and it would dehumidify in the summer. It would heat in the winter, and it would cool in the summertime, and it would do it within a range of values, and it would do that in a rational way. And it would be coupled with a heat recovery ventilator. And that would be a really nice thing to have.
Okay, so I'm in. I'll be an investor on the Lou Harriman project here. This is what you're saying, is that the technology exists, but the product itself does not exist. Is that correct?
That's exactly correct.
Why? What is people's problem that we don't have? And we've got all these manufacturers making all this stuff that they want to sell to us. Well, they make something that we actually need, especially with the codes going in place. Like, who do I need to knock on their door and tell them that they're being an idiot?
Nobody. Everybody is responding to rational cues from the marketplace.
Ouch. You hear that, homeowners? It's our fault again.
It is, because it's very difficult for a homeowner to say, gosh, I don't have enough fresh air in here. And gee, I know what my problem is. I have, 45 cubic feet per minute instead of 150 cubic feet per minute in this space. We don't have easy metrics that give us the visual and sensory feedback to say, I need something different than what I have, because we have a very broad range of tolerance for this stuff as human beings.
You just brought up metrics, which is one of my favorite topics. So do you think that now that people, the younger generation of homeowners are having on their smartphones, they've got the data on what temperature their house is at and when their furnace is running, do you think that absolute humidity might absolutely get into the graph there that the homeowner is looking at, and maybe that metric will help to drive the market of inventing the products that they will want to buy?
Well, I sincerely hope so, but that's probably a false hope in my case. I have spent pretty close to 40 years in this industry, and I know that it's very difficult to educate people about the complexity of dew point versus relative humidity. So I think it's going to be a tough sell. I am vaguely optimistic. Well, not vaguely. I'm 30 or 40% optimistic that what we might have in the future is a thermostat on the wall where you have a dial. It's a big, like, Frankenstein knife switch kind of dial. You know, you yank it back and forth between two extremes, and one says cooler and the other says drier. And if you had that instead of numbers and exactly dew point, and then the system was intelligent enough to make sure that it actually took moisture out of the air when it needed to, add it when it needed to, do cooling when it needed to. When you respond to your sensory inputs, it says, "Gosh, it's too cold in here," you know, as opposed to, "Gosh, it's muggy in here. I better make it colder." You know, which is not effective.
What if we just took the thermostat completely off the wall and we had a voice recognition system that just listens to you complain, and based on the tenor of your voice, it would say, "Oh, good, it needs to be a little."
Nah, I don't think so. I like the idea of a physical dial that with divisions but no numbers, and it says cooler or drier.
Cool. To empower the homeowner to actually feel like they're participating.
And to avoid focusing on the numbers, because people, if it is drier, will be more comfortable at a higher temperature. That will save energy, and that will make them more comfortable. Similarly, in the wintertime, if we add a little bit more humidity, we can be cooler, we can be warmer, more comfortable at cooler temperatures, and that will be a good thing. So I think if we can get thermostats that respond to sensory input and get the unproductive numbers out of people's minds, I think that will offer a lot of improvements. But we have to have equipment that will respond to that. We can't have equipment that when you ask for drier, it makes you colder. And that's some technology that requires some work.
Yeah. So the other division that we originally opened up this episode with is the drying of stuff. What principles do we need to know about the drying of stuff in order to be effective?
I think the most important thing about drying stuff, when I say stuff, I'm talking about, gee, the carpet's damp over here. Or, gosh,
why is that carpet damp over there?
Why is that carpet?
Where is that dog?
Because, yeah, where is that dog? You know, you got a pipe leak, and now you fix the pipe leak, and so now you need to dry something out. You had a problem with the air conditioning, and everything got really muggy. It was either too cold or something, and now you got this damp feeling. Your sheets are damp. You need to dry stuff out. Well, I think that the most useful principle to keep in mind, something that very fine engineer told me a very long time ago, is you got to get the heat in to get the moisture out. You have to add energy. You have to add thermal energy to a damp material in order to mobilize that moisture, the water molecules that are in there. You have to get them moving. You have to get them moving so more of them will come to the surface. It also helps a lot if you happen to have dry air in which to put that humidity so that it will absorb that moisture.
And maybe move the air a little bit over the material?
Well, the reason that you want to move the air over the material is if that air is dry, you want to do that. If that air is humid, you don't want to do that. Because if the air is humid, then you might be adding moisture to that damp material, not subtracting it. So you want dry air, and then you want to move it across the surface. You don't want to move it too quickly because you don't want to crack wood, for example, if it's moist. You don't want it drying really quickly, but you do want to have air movement across it so that you can pull the humid layer of air off the surface, but not do it too quickly.
Could you also raise the temperature of the air that's around it, which would lower the relative humidity and turn the air into more of a sponge, or is that a kind of ineffective? I mean, is that a...
Nope, that's not a bad way to do it, as long as you aren't creating some counterproductive, phenomena at the same time.
Like what?
Like, for instance, you got a damp area, so you're going to heat up that area with the hairdryer or something. Okay, so then you're going to mobilize that moisture. It's going to come out into the air. It's also going to be driven deeper into the building, too. So maybe it would go to another part of the building and condense there. So you do need to think a little bit about that. When you mobilize the moisture, it's going to go places. I'll tell you where it's going to go. It's going to go everywhere. But it's going to stay in the areas that are still cool. Why is it going to stay there? It's not going to go there because it's seeking the cold. It's going to go everywhere. But when it gets to the cool area, there's going to be less energy there. So it's going to want to stay there. And that's the way to think about this business of humid air and humidity and dew point and relative humidity and stuff like that. Think about the fact that when you have a lot of absolute humidity in the air, or even a little bit, it's going to go to the coldest place along with every other place, but it's going to stay in the cold places. That's the way to think about it. Not that it's going to go there like it's on a mission to get to the cold place. It's going to go everywhere. But it's going to stay in the cold places because there's not as much energy there to lift it out and keep it moving and keep it in the air.
First of all, I'm in for all the products that are in your head. I hope that we get to hear a lot more about your ideas and see them actually come to life in real life. Lou Harriman, thank you so much for talking with us today.
You're very welcome. It's a lot of fun, Corbett, as always.
You have been listening to the Building Performance Podcast from the Building Performance Workshop. I'm Corbett Lunsford. Tune in next time.
Thank you for listening to the podcast. Thank you so much to Corbett Lunsford for being willing to allow me to re-air this episode. You can find all of his podcasts by looking up the Building Performance Podcast, and you can look up buildingperformanceworkshop.com for everything that he's up to. I highly suggest that you follow Corbett. If you are willing to give him or listen to his podcast, give him a review, or just give him a review on his podcast just for enjoying what you had here, I would greatly appreciate that. He's building an audience. He's doing really good things to help the community, and I would encourage you to support him in what he's doing. Also, look at his book. His book is really, really good as well. It's like really the Bible on building performance. Especially, it's written in a way that an HVAC technician can understand, in my opinion. Now, we're all the way here at the end, so I'm going to give you a message here that's just for those of you who listen all the way to the end of my podcast. And I assume that that's a reduced number from those who start off listening. And that message is that I know some of you probably hear the sponsorships, Rector Seal, Testo, Carrier, and you think, what gives? Now Brian's going to start pitching products. I want to tell you that I work with companies that I use. I work with companies that I believe in and I believe are doing the right things for the trade. The partnerships have to make sense. And with all three of these companies, the partnerships make sense. Now, does that mean that they're going to get it right every single time? Does that mean that every Testo tool you've ever used and every Rector Seal product that you've ever touched and every Carrier unit you've ever worked on is going to be perfect? Absolutely not. But what I want to give these companies credit for is that they're stepping up to the plate to help with technician education, and that really is at its core what HVAC School is all about. I mean, we have a lot of fun, I joke around, all that type of thing, but you'll notice we keep it positive, we keep it pro-trade, and we're looking to improve technicians. That's why we're technicians first. We're for techs, by techs. Sure, do we help out some apprentices? Do we help out people who are in trade schools? Absolutely. Do we help out homeowners? I hope not. This isn't for homeowners. This is for you as a technician out there in the field. I try to do things in such a way that it's going to be over the head of a homeowner, but it's going to really serve the technician. So the reason why I take on sponsors is because it's a necessary part of helping this grow and helping me create the very best content that I can. And when I pick a sponsor, when we choose to work with a sponsor, we're choosing people who have shown their commitment to the trade and who I'm proud to represent. Am I going to be a little rah-rah sometimes? Well, sure. I mean, first of all, because I talk about the products that I believe in. But second of all, because I really like these companies and I really want to see them do well. I want to see Carrier, Testo, and Rector Seal do well. And do I give them feedback sometimes that says, hey, maybe you should adjust this or maybe you could do that? Absolutely, I do. Am I going to do that here on the podcast? No, I'm not going to do that here on the podcast. I don't need to. I talk to the people inside these organizations when I see something that they could change or adjust in order to make it better. But the fact that they partner with us says a lot about them. It really does. And I'm very thankful to them. And I'm very thankful to you for listening more than anything else, because you're the one who makes this whole thing work. The teamwork makes the dream work, as they say. All right, I'm done being cheesy. Thanks for listening. We'll see you next time on HVAC School.